同学们，大家上午好。也欢迎线上的各位老师们、同学们参加今天这个英国帝国理工学院Guillermo Rein 教授的这个学术报告会。那么 Guillermo Rein 教授呢是我们实验室的老朋友了啊。I just said that you are the old friend of my lab for many years. 那么我现在 please allow me to introduce in Chinese so many people can understand. Guillermo Rein 教授呢是英国帝国理工学院的教授，然后他他是国际燃烧学会的会士，是国际消防工程师学会和美国消防协会的联合会刊，大家也都非常熟悉的 Fire Technology 的主编，那么也是这个国际燃烧学会会刊Proceedings of the Combustion Institute 的副主编，以及 Safety Science 的这个期刊的编委会的成员。Guillermo Rein 教授呢是帝国理工学院的这个 Has Lab 的研究团队的创始人，他的研究方向呢包括这个固体因燃机理、森林火灾蔓延、建筑火灾蔓延等各个领域。那么在过去的10多年当中呢，也有中国的很多的同学们呢都在 Guillermo Rein 教授的团队来开展这个联合的研究。那么他主持编写的专著2部，参与编写专著6部，共发表期刊论文140余篇。那么会议论文呢是250余篇，他的引用呢达到了11000余次，他的 H 指数是57。那么他的研究项目呢获得了这个欧洲研究理事会巩固基金，就是 ERC 这个的 grant 的这个资助，以及英国工程和自然科学研究委员会、中国就是大家很熟知的 CSC 等机构的资助，研究资金呢累计达到超过500万英镑。那么它特别呢是因燃这样一个研究方向，因为大家知道因燃既是火灾研究的重要的方向，也是燃烧研究的重要方向，是这样一个领域的国际的权威学者。他率先提出了像这个 traveling fires 像这个等这样的一些包括这个 forecasting 这个 fire dynamics 等这样的一些工程概念。他曾经获得2020年国际燃烧学会卓越研究奖，2018年国际消防工程师学会的这个 Goose 奖章，以及2017年英国工程师杂志合作创新奖，2016年国际野火学会的青年科学家奖，2022年帝国理工学院总统卓越研究奖以及2016年国际消防工程师学会的 Peter Land 奖章，以及2009年国际燃烧学会英国分会的这个奖章等诸多的荣誉。那么这是这个 Guillermo Rein 教授的简历。那么 Guillermo Rein 教授呢，他跟我们实验室呢有很多的这样的一些合作。在10年前，实际上 Guillermo Rein 教授曾经访问过我们实验室，所以转眼就是过去了10年啊。那么我们也希望通过 Guillermo Rein 教授的访问，能够进一步的来促进我们跟帝国理工学院在火灾研究方面的合作。那么下面呢，我们就热烈欢迎 Guillermo Rein 教授给我们做学术报告，大家欢迎。
Thank you so much. Thank you very much for this invitation, for this presentation. And I'm delighted to be back. It's my second visit to Jefe. The previous one was 10 years ago. But my next one will be much sooner than 10 years. So I look forward being here. I've been practicing my Chinese, so ni hao. And I'm going to be talking about a topic that I think is important to many of us, the topic of fire science and the context of modern ideas like fighting climate change and sustainability and net zero. These are big words that many universities around the world pronounce. But my name is Guillermo Rein, and I am from Imperial College in London. So I don't know how many of you have been to London and to visit us. This is an official invitation for all of you to come and see us. We are in London, in central London. So if you go to the museums like Natural History and Science Museum, Victoria and Albert, and Hyde Park, then we are literally just there. Very recently, we were very happy that QS rankings put us second in the world next to MIT. We're very comfortable next to MIT. Everybody's very happy to be next to MIT. Mix of students. It was signed in 2021, and it is between my department, the Department of Mechanical Engineering, is one of the biggest departments of mechanical engineering in the world in terms of size, with the state key lab of fire safety. So it's important that we continue working on this and we continue the exchange. And I look forward, many of you in the room and online, to continue this exchange. So a little bit about me. You have already noticed my accent is not very British. So that's because I was born in Spain. So my accent is Spanish. It's very thick, but it's okay. Hopefully in a few minutes you will start to get it. I left Spain. I studied engineering in Spain, mechanical engineering. I left Spain to go to the United States. I studied in California at the University of California, Berkeley, where I started to do fire science. I was working for NASA, taking care of the safety, fire safety of a spacecraft. And then I went to the UK, first in Edinburgh and then at Imperial, to become an academic. So now home is the UK, and I want to stay there for the rest of my life until I retire. But I just wanted to know this little triangle, and now today we are here. So a lot of movement in the Northern Hemisphere. As also already mentioned, I'm very proud, tremendously proud, to be the editor-in-chief of Fire Technology. This is one of the leading journals. That we have 4 journals in fire science, and then we have other disciplines that also do fire science. But of the ones that only do fire science, this is one of the leading journals. We are the oldest journal. It was created in 1965 and continue publishing. So there is a lot of history. When you go into our online archives, you have access to all the fire science since 1965. So not just the latest papers, but you have also the papers of our founding parents, which is important. We are associated with the NFPA in the United States, the National Fire Protection Association, and the Society of Fire Protection Engineers. So we are their scientific journal. We do science to make sure that it's used, right? And whenever we look, we can look into submissions, we can look into downloads, we can look into impact factor, we can look into the site score. What we are seeing is that the journal is buoyant, is succeeding, is going up. So I want to highlight one of these steps. Look what happened here. You know what happened here? And then it took off, that I visit Jefe. So my expectation is that after this visit, right, I'll be here. Okay, so when I come back, I hope the journal is up there, right? Thanks to actually USTC, you are really important. I mean, you know this, but I'm just going to tell you. Your institution, all of you, are really, really important for fire science in the planet. You are the biggest fire group. You are my favorite partner, actually, in the world. The amount of work that you do is incredible in quality, style, impact, and value. And if this journal were to continue succeeding, it has to include you. So the more of USTC that we have in the journal, the better the journal does, and then you get the impact factor and the qualities that you need for PhD thesis, graduations, and promotions and projects. So I'm asking officially for an investment of USTC into the journal, and then the journal will give you back what you want, because you are so big that you are almost a quarter of at least a third of the fire science community. So please know that we have 2 associate editors in the journal, and we get papers from USTC, but I know that the best papers of USTC go to other journals. So I want to attract us into this journal. I want this to be home for you. So now we're going into the topic. Obviously, didn't do all these things without the amazing help of my group. Many familiar faces here that I saw yesterday, my Chinese former students, Xinjiang Huan, now a professor, associate professor in Hong Kong Poly, Uchi Hu, he's now in Chengdu, Han Juan, Seng Wen Hu, Suan Se He, Uchan Kui, and we have, I saw them yesterday. They flew from different parts of China, and I saw them yesterday, and it was really nice because I haven't seen them in such a long time. So it was a very nice reunion of my group, and I look forward having more of them here, right? So when I come back in my next visit, there will be a new row with more Chinese students in it, hopefully. So let's start. So we are all involved in science. One of the joys of doing science is this journey of discovery. We discover together with our teams and our colleagues and our communities, we discover new things. This is what science does. Discover things that were there, we observe them, we do computer models, we do experiments, we develop new theories and new understanding. And it's truly the joy of scientific discovery. Now, obviously, it doesn't come without difficulties. The exhaustion of the trip. Very often we look in the wrong place. Sometimes we think we found something, but we didn't. But at the end, when we look back into our careers, it is a journey of discovery. As an engineer, not just as a scientist, we also believe in creating these wonderful things that engineers do. These things that nature would not do. This is what engineers do, things that otherwise would not exist. And these things bring comfort to society, allow civilization to progress, development, and safety. And the combination of the two of them is what we do as professionals. And always, once or twice or three times with our careers, we find our own disciplines, no matter which one it is, at crossroads. Crossroads is that you're having a journey and suddenly you have an option that we didn't expect of changing directions, of changing the way we thought we were going to do things, because things have happened in society, things have happened in our field, things have happened in our lives. So crossroads are something really important to keep an eye on in every issue, things that we do in life. In our field of fire safety, especially coming from combustion science, we are facing some big crossroads. When I started into this field, these crossroads did not exist. So these are very modern and are really important. Not taking these crossroads could have significant consequences to our field. Some of these crossroads are big things like fighting climate change and adapting to climate change, net zero, and the ability of different authorities, governments, and institutions to help us balance the amount of carbon in the atmosphere and to have cities and a world that is sustainable not just for us, but for the next generation. So these big things, when I was a student, did not exist, and these things are important. These are crossroads. So we, as fire scientists, need to decide if we take these crossroads or if we just continue without looking for this topic. So I'm suggesting today that we fully look into these crossroads. And I know, for example, that USTC is leader into looking into these crossroads. So the things that I'm going to be mentioned today are things that USTC and the State Key Lab is already doing. This is just related to something that is very important. I don't know if I like it a lot. In psychology, there is a concept of Maslow hierarchy of needs. Maslow was in the 60s. He was actually an engineer. They came out with the realization that this is where we want to be, all of us, every single person in the planet. We want self-realization. We want our dreams to come true. We want our happiness to develop. We want our families to be there, right? In order to do that, we have to be recognized. We have to work in society. We have to be safe, and we have to have our psychological needs. This is that we are able to drink and to sleep and to eat. So this is very foundational. If we don't have the foundations, we cannot realize ourselves as individuals, right? and social needs are here. I know this is very important for China. But look what is just below, between us in society and us being able to eat. In between them is safety. If there is no safety, if our communities, our societies, our countries don't feel safe, they cannot self-realize. So this is a very important pyramid, and it shows you how safety science and fire safety is at the core of human development. Without this, there is no point to continue working forward. And in the course of fire safety, we've always been fighting against the problems of fire and toxicity and all the problems that flammable substances, being solids, liquids, or gases, produce. So this is the topic that we are discussing. I'm now from London. No? My family is from London. I live in London. In London, as every other country in the world, we have a big fire that everybody relates to. Every single nation in the world is able to refer to a fire. In London, we teach our kids about what happened in 1666. That was a long time ago, because it was a fire that wiped London. 3/4 of London were gone. It literally almost, they were lost. The whole city was lost. It was very dramatic. It happened in 4 days, and it became a historical event that now is taught. It's in the books, and it's taught to kids. So my kids, for example, because they grew up as Londoners, they were taught the Great Fire of London of 1666. It redid London. So the modern London that we know now is different because of what happened in this fire. But there are many lessons that should not be forgotten. Every country goes back to their fire and their lessons, but these are important things. And for us in London, what happened in 1666, we're there. So then we're talking about combustion science is the understanding of how things burn. Put it into my context. Now, many of us are fellows of the Combustion Institute, where combustion science happens at the global level. We are talking about safety. We mentioned the importance of safety for self-realization of society. And the intersection between these two worlds, this over here is fire research. That's us, right? How important it is, right? Combustion and safety is a sizable topic. Will always be there, and there are so many things that need to be done. We're going to be busy with it. And then we have the crossroads of society: climate change, net zero, and sustainability. The intersection of these 3 topics is what I want to discuss today. The fact that we are doing combustion for safety in a modern environment. So this thing over here, which is a sizable amount, is us bringing attention to modern topics that society are demanding from us to bring them safety based on the knowledge that we have of fire. So this is what all of us are doing. So the 3 topics that I'm going to be, obviously this could be a whole week of discussions of how fire affects sustainability, but I've decided not to. Next time, hopefully you will invite me for a week of lectures. If not, I'll just talk about 3 topics and quickly discuss things forward. So the first one is going to be wildfires. Why is wildfires into this modern view? Timber and batteries. And as I speak, I know USTC is world leader in the 3 of them, and it has really important research that is happening in the past years and as we speak on the topic. These 3 topics, wildfires, timber, and batteries, is just 3 examples that I chose because I happen to be active on them. But there are many, many more. Maybe we can discuss it during the questions. But there are other aspects, for example, facades, insulating facades, green walls, wind turbines, solar panels, nuclear power plants. Just think of anything new that has arrived as an innovation to society. It always, unfortunately, has a fire hazard associated to it. Sometimes we recognize the fire hazard right away, maybe in wildfires. Sometimes we actually struggle to recognize the fire hazard. So maybe this happened with batteries. Batteries have been with us for 20 years, and it took the battery industry a really long time to recognize publicly that they have a fire problem. So now we know they have a fire problem. But it took a really long time for them to be embracing safety. So we start with wildfires. Now, the context of wildfires that we are happening is wildfires have been happening in the planet for millions of years. We became a species, the human species in the planet, and there was already wildfires burning. And we humans learned wildfires from nature. So we became the first species in the planet that instead of running away from wildfires as every other species of animal does, we became the only species that turned around and started to investigate what is this, right? Probably our ancestors burned their hands and their hairs and everything. And fast forward, now we have power that is arriving to us through the taming of fires and the metallurgical processes, the chemistry, the comfort of heat. Is a success story. But wildfires continue burning outside our towns, the natural cycle of wildfires. When we look into what has happening with wildfires, for example, we can identify, this is a nice set of data from the United States. It's a very old plot, but it's okay, it still works. It goes down to 1985. It actually captures about 30 years of wildfires. And we could look into the blue. The blue is the number of wildfires that were detected in the United States of America that specific year. I use the US because it's the best database that we have. I wish it was Spain or UK, but no. The best database on wildfires is the Americans because they've been looking into this for longer with all their abilities. So we see that the number of wildfires is insane. We're talking about 100,000, but it actually is not changing. It's just going up and down, up and down. So when we look into the number of wildfires, people say they have always been there, right? We don't have to worry. They've always been there. We will do as we were doing, and we don't have to worry. But that's the number of wildfires. That's saying that a tiny little wildfire that burns half a park is the same as a wildfire that burns 7 towns. That's not fair. No, we have to be able to identify the damage that the wildfire produce. How bad are these fires? So then we can go to the next level. That's the black. Is, for example, a proxy to damage is the size that the fire burned. It's called the burn scar, and it can be measured in kilometers squared, thousands of kilometers squared. And then now what happened? Going up. And actually, since the database has been captured, it actually goes all the way up. So what we see is that wildfires in number might not be increasing or decreasing. The damage they produce is really high and exponentially. We always worry about exponential and exponentially growing. Take into account that the bigger the fire is, the more people they're going to be affecting. If you have a small fire, maybe it's affecting a few houses. If you have an absolutely massive fire, you might be capturing thousands of homes, maybe actually even millions of people capturing in the burn scar. So we as engineers, we are very concerned about this trend. And officially now, even though I know the government of China is very concerned about what is happening with wildfires all around the world. I'm referring to the US database because it's the base one in the world. This is happening all around the world. I am not aware of any sizable country in the world that is not worried about wildfires. I'm not aware. If you're aware, let me know, because every single country that I go, they are worried about what is happening with wildfires in their country. And then obviously when we have something like this, everybody, at least in my world, says, oh, it's climate change. It's climate change. This is caused by climate change. Well, the answer to that is yes, it is climate change, but it's not just climate change, right? So this is what I'm bringing this question to you because it is climate change, but it's not just climate change. It's more things. For example, there are also changes in the land use. For example, virgin forests in the Amazon that has been a jungle untouched by humans for thousands of years. Suddenly now they're being used for harvesting the wood, or for plantations that are being developed in virgin forests. This is also happening in Southeast Asia, in Indonesia, where the Indonesian jungle now is being used for plantations of oil palm. So changing the land use typically changes the fire behavior, and it does it always to the worst. It's interesting that when we humans go into a pristine forest, it's not to make it less flammable. We always actually, when we go into the forest, we make it more flammable. So there are changes that are caused of land use. There are also changes in population. People are moving in and out of the forest. We are more familiar with people moving into the forest, as it happens in the United States. People in the US love to live in the forest. But maybe you're not familiar with the fact of what is happening in Europe, which in my home country in Spain, where people are still abandoning rural areas and they're moving into the city. When they do this, they are abandoning agricultural land that has been agricultural for maybe 6,000 years. So suddenly, for the first time in 6,000 years, no one is looking at the land, right? They're abandoning it. And then when we abandon the land, typically it actually starts to become more flammable. So there are changes in population, land use, and climate change. And then we have the more strange of all the changes. Is what is called fire exclusion. This is the most concerning and most difficult to be aware of. And is thanks to the Americans, to North America, we know of the concept of fire exclusion. Fire exclusion is that if we exclude fire from the forest, if we became so good as firefighters that we fight every fire and we stop every single fire, then what we are doing is making sure that the next wildfire is even bigger and bigger and bigger until our capacity to extinguish is overwhelmed and we actually end up with an absolutely immense wildfire that in a way we, by fighting fires, have created. This is uncontroversial scientifically speaking now. When it was put forward the first time in the 70s, government in the United States thought that scientists were crazy, and they literally said, scientists, what are you talking about? Obviously, you don't know how to collect data. It cannot be the more that we fight, the bigger the fires get. That doesn't make any sense. It's the other way around. The more that we fight, the smaller they get. And now we understand, after 50 years of research, that if we fight the fires, if we exclude fire from the environment where it was created by nature, we start to accumulate the fuel. It doesn't burn, it accumulates. It doesn't burn, it accumulates, and then ends up with so much fuel that when the fire arrives, it becomes a humongous fire that we cannot stop. So the concept of fire exclusion happens in the United States. It might be starting to happen in Europe, in the south of Europe, in the Mediterranean. It might start to be happening in Australia. But it's a lesson for everybody. Hopefully it will never happen in China, that we should not just fight the fires. We need to understand and manage the fire, not just fight them, right? So all these, and it's a mess, right? Because very often, actually, everybody's here. I bet big parts of China are here, big parts of the United States are here, big parts of Europe are here. And when you're here, you don't know why is this happening? Well, it's happening because of this, because of this, because of this, and because of this. So it's very messy. But that's why we, as scientists, study fires in the Arctic. This is the Arctic Circle. That is going to be United States, and that is going to be Europe, and this is Asia, right? So this is the Arctic Circle seen from above. So I'm from Spain. I like warm weather, like Jefe. I don't like the Arctic. It's too cold for me. But as a scientist, I study what happened in the Arctic in wildfires, because in the Arctic, there is no people. In the Arctic, there is no use of the land. In the Arctic, there is no firefighting. So what happens in the Arctic is climate change. That's the Arctic. So when we see changes in wildfires in the Arctic, we are studying climate change and wildfires. And what we see in the Arctic is that unprecedented number of wildfires, increasing in frequency, increasing in size, increasing in damage. And that means when we study the Arctic, everybody can learn about what is happening because it gives us this big bubble of climate change. Some of the topics that we study in the UK in my group is because of the Arctic, because of that reason. I isolate the signal. But the Arctic or not the Arctic, we are looking into protecting people. We are scientists, we are engineers. It is absolutely paramount. I already mentioned this, but it's important to protect people. These are examples of failure of protecting people. In this case, this is a California town. A wildfire arrived from the outside. It crossed the interface between the wild and the urban and started to burn the homes. It became an urban fire caused by a wildfire. And every year, all around the world, even in China, there is about 1 million, at least 1 million people that have to leave their house running because a big wildfire is arriving to their house. It could be an isolated home, it could be a community, it could be, as it happens in London later on, you will see inside the city itself. At least 1 million people have to evacuate. So these communities were evacuated. We're very happy that in this particular photo in California, no one was injured. But when they came back, they had no homes. They had lost their homes. There were no schools for the kids. There were no hospitals for the community. So these fires are wiping out. They're destroying whole communities that have to be rebuilt. And it's very dramatic to lose your neighborhood, your town, your hometown, your city. So this is what we are trying to fight. The amount of damage in California, for example, is really, really high. California right now has to pay in the order of billions every year to reconstruct what the wildfires are happening. This is just California. In reality, it's happening all around the world, but it's quite dramatic, the need for fire safety engineers to help with this. I just want to give you two more examples. One is London, ourselves. 19th of July, 2022, London, I was there. It was a very specific day. There was a heat wave. London is not supposed to be very warm. It's now getting really warm because we are having heat waves. They think it's because of climate change. Very specific, very strong heat wave that led to about 400 wildfires. Not fires in buildings, wildfires. These were not cars, buildings, or homes. These were the gardens, the parks, the green spaces, the recreation and the trees in the city, inside the city. This was not in the wilderness fires that arrived to the city. These were fires that happened in the city of London. Right? For example, I was very close to this one over here. I remember I was with the kids at home and I could smell, and I said to the kids, today London smells like the fire lab, my lab. But that's wrong, right? Home should not be smelling like fire lab because the fire lab is where we burn things for research in safe conditions. Having that smell close to home made me feel very unsafe. They were all burning around London to the point that the London Fire Brigade, one of the biggest fire brigades in the world, the 19th of July was the busiest day since the Second World War. So I don't know if you're familiar, but during the Second World War, London was bombed on a daily basis, and it was burning the city on a daily basis. So that day in July, London was at war with wildfires. And this is a lesson that should not be forgotten. Not many cities have felt this. We don't know why London felt this that day. Why did a heat wave do this? It really happened. It was not a dream. It was not a nightmare. It's in the data. And this could be a tale of things to come in the near future. These heat waves that bring what I call now fire waves into cities that are not prepared for this. Another strange phenomena happened the year after, so that was last year, in Hawaii. It's not that far from here. Hawaii, the former capital of Hawaii, Lahaina. It was an ancient town, beautiful in one of the islands. And in the summer, it burned. It was a wildfire outside the city that moved into the city. It completely destroyed the city because it happened at the same time as a hurricane. We don't know many cases of this. We don't know many cases of a hurricane driving a wildfire and having a wildfire with hundreds of kilometers per hour of wind. It leads to beyond wildfire, extreme wildfire behavior. It becomes actually something that it cannot be observed with the means that we have. The outcome is an absolute 100% destruction of the city. Even the ships in the harbor of Lahaina, even the boats were burned with all the heat by convection and all the embers that the wildfire was bringing in the direction. So literally, absolutely everything was burned, and many people were talking about one of the highest casualty rates in the United States wildfire history that happened. Lessons need to be learned. It happened under US. Everybody can learn from these behaviors. Engineers, we need to protect people, property, and the environment as well. So what can we do? And what is USTC already doing? And what is it that we are doing at London and many other fire groups around the world? Well, we are doing all of the above. We are doing experiments. We are doing experiments in the lab. We are doing experiments in the field. We are doing development of theories of why wildfires behave this way, what is the ignition spread, what is their emissions, how we can suppress all of the above. And then we develop computer models, theoretical models or computer models. This one in particular is just a very famous equation that was developed for farsight. And we combine all this. We do all the things that are already happening and we put them together, experiments, models, and theory. This is the circle of fire science. We need to do all of the above. Some people just do experiments, fine. Some people just do models, fine. Some people just do theory, fine. But all together is what brings solutions and understanding. It cannot be that one community just with one approach will lead. It has to actually be all of us coming together in a cooperation, in a sisterhood and brotherhood of approaches. And what we are already delivering and what we will continue delivering to the people that are waiting for us, so we provide safety. Well, it's a long story, but I like to tell this story in the concept of the layers of our protection. So in this picture over here, we are seeing already the things that we can do to protect. For example, first, and this goes in order of chronology, we can prevent the fire. We can prevent the bad fires. And remember fire exclusion. If we only prevent, we end up in a worse situation. So we need to avoid ignitions, but we need to promote the good fires. In wildfire, this will happen in the building. In the building, no fire is good. Just avoid. In the forest, we avoid the bad fires. We promote the good fires. Good fires are the fires that have the right intensity and the right frequency. And if they have the wrong intensity and the wrong frequency, they become bad fires. So prevention, very important. I'm not saying prevention in simple terms as don't play with a match, don't bring a lighter here. I'm talking about technical prevention, theoretical prevention, which is a probabilistic way of saying ignition sources have power and frequency. Fuels have a distribution of flammability, and you don't want the two of them to intersect. Ignition power to find highly flammable fuels. That's the worst case. So you want to separate the ignition and the flammability of the fuel. If we have failed in prevention, that's a breach of the first layer, then we have more layers to help. It's not the end of it. Okay, there is 6. Just there is a wildfire. It's a bad wildfire. We could not prevent it. First thing that we do is to detect as soon as possible. The earlier our detection system, the more things we can do. Detection per se doesn't do anything. Detection per se is a layer that allows all the other layers to kick in. So we need to detect. We need to know that this is happening. We can use satellites. We can use watchtowers. We can use people in the forest, people that are living in the forest. We can have drones observing this. We can have many different ways of detecting. One thing that we can do, we can suppress. This is the most popular. I mean, you're fire scientists, but this is what people think that's the only thing that we can do. So if you go outside this campus and you are a citizen, they think that the only thing we can do is suppress. The only thing you can do when you have a wildfire is call the firefighters. But we know we can do more. Suppression is really important, but it's just 1 out of 6. And suppression is put down the flames, right? Another thing we can do is compartmentalize. It's a complex word. Is to create compartments, even in the forest, in the sense that one forest, one site, one region is burning. We should not allow the fire to jump from one site to the other. We should compartmentalize, either ahead of time, what is called fire breaks, and sometimes highways can act as fireways or rivers and even valleys, or maybe we do the fire breaks in real time, which might take 1 or 2 days. Okay, but compartmentation is very important, and combining the two is fantastic, right? Compartmentalize and suppress. And there are 2 more. 5th, very dramatic. I already alluded to this. Sometimes we have to evacuate communities because we cannot prevent it, we cannot stop it, we cannot compartmentalize it, but we have seen it. So we need to take people away, evacuate communities. We're talking about by the thousands. This is a topic of research that is very active. And the last one is brace for the incoming wildfire. We have failed stopping this wildfire. Hopefully, we have evacuated but the wildfire is coming. Now we need our buildings, our communities to be resilient and strong and be able to contain the damage. There is going to be damage, but hopefully it will be not too much. Hopefully the community can recover, fix, mend, and come back to life again after the wildfire. And this is in order of chronology. Prevention will be the first damage. In the cases that I told you before, the Lahaina and Hawaii and London, all the layers fail. This is what is called a worst case scenario, breach of all the layers, right? Cases that we don't know about are cases where prevention was not breached. We don't even know. If the fire didn't happen, we don't hear the bad news. It's quiet. Quiet is good, right? Or maybe the fire happened and it was detected and then it's suppressed. These are case studies that we can think of. Second topic, sustainability. Sustainability is a balance between the environment, equity, and economy. Equity being fair. Being fair not only just with us, but being fair to the next generation, which will inherit whatever we do, for good and for bad. So sustainability is something that engineers have been doing for a very long time, but they didn't know that they were doing it. And now we've been asked to do this explicitly. So for example, one way of doing sustainability is not to only build in steel and concrete. We can build beautiful buildings out of steel and concrete, but we have discovered that sometimes steel and concrete are not as sustainable as we wish them to be. So one of the ways to build cities that are sustainable or buildings that are sustainable is to make them out of wood. We humans have been making homes out of wood for millions of years, right? Our first homes were actually made of wood. They're not in the historical record because wood degrades and it doesn't leave anything. And then we started to build in other materials. But it's not a revolution. We've been building with wood for a long time. Now it's high-rise buildings, skyscrapers, tall buildings made of timber. That is what is unusual. For a very long time, this is an example in Norway. This is a high-rise building made of wood. It's not that the exterior looks wood, it's that the structure, the inside, the load of the building is being carried by wood. And that requires what is called engineered wood, mass timber, in particular CLT, cross-laminated timber, which is humans improving upon the trees, realizing that trees are amazing, but not perfect, because they only carry loads in one direction, whereas the engineer needs the structure elements to carry the loads in two directions at least. CLT and mass timber does that. So now it is possible, structurally speaking, to build out of timber. What happened? This is an example of CLT, right? You are combining loads in two directions. So this block can carry loads in two directions, whereas each of them, which comes from a tree, can only carry load in one direction. It's CLT, engineered timber. The problem is that timber is amazing, it's beautiful, we love it, captures the carbon neutral, inexpensive, people like it, right? This is actually wood, it makes us feel comfortable, the view of wood, but it's flammable. All good products known to humanity are flammable. Some of them are very little flammable, some of them are extremely flammable, but there is a need to understand the flammability of wood products. This is an example of what happens in time if you have a block of wood and you expose it to a fire or to heat. Right? It starts to degrade. You start to have wood that dries, and then it chars by pyrolysis, and then this char might actually oxidize itself by smoldering and disappear. So at the end of the day, what you end up is you lose timber. So not only is flammable and creating a fire and creating a hazard, and having people to evacuate and be away from fire, is that the structure is losing section. And engineers know that if you lose section, you lose the capacity to carry loads. So now the structure is weak and it's a high-rise building. So it is a concern. And that means that high-rise buildings made of timber can be done, but they require the highest and most advanced fire engineering that we can get, because it is really difficult to get it right, because it's more flammable and it actually, the structure is weakened by the fire. How will we do this? Well, We would do all of the above. We would come out with experiments, we will be measuring, and we will coming out with solutions to the structure. These are the multiple steps. We have also computer models, and we have ability to calculate. And at the end, we end up is creating guides based on science that engineers can read. For example, this is a very famous guide in Europe. It's called Eurocode 5, and it's a guide that teaches structural engineers how to design in wood. And the Eurocode 5, which is a book that is revised every many years, has a significant section on fire. And it teaches engineers what they have to do to calculate timber in fire. And that chapter, the fire chapter, keeps getting thicker because the science that we are creating is being fed to the engineers, and the engineers are learning how to do this better and better and better. And at some point, the safety of their methods would be that we can have not just tall buildings, but very tall buildings, because we will be confident that they can be safe. And we will be able, sorry, we will be able to have experiments combined with models, as we did with wildfires, and we will end up with something as pretty as having the charring rate as a function of time, evolving in time, and being able to have experiments and computer models agree with each other. So it's not just that the experiments are important, it's not just that the models are important. The emphasis here is the circle of the models and the experiments, talking to the engineers and coming out with improved ways of calculating are essential. And we will help in how to prevent fires by understanding the flammability of wood, how to detect fires in a building that is more flammable than normal, how to evacuate. In a building, we know that whenever there is a fire, we evacuate immediately upon detection. So in wildfires, detection was here. In a building, evacuation is something that we do very quickly, as we can see with examples of design over here, right? Compartmentation is really important in a building made of timber, because the compartmentation will, in time, be breached by the charring rate and the loss of section. We should be able to suppress, especially if it's a high-rise building, we might need to suppress, so the fires above in floors top where firefighters cannot reach can be suppressed as well, and that the building does not collapse due to fire, that is able to absorb the damage, and that we could rebuild, mend, or fix the building made of timber upon it having a fire, right? This is a hot topic of research, and I know many people in this group in USTC do timber research, because engineers realize they cannot do this they can do this really well with steel and concrete. They cannot do this as well yet with timber, and they need science, so they need all of us to help them. The last topic, and I know this is the home to one of the best sets of research that exists in the world, battery fires. So this is related to net zero. Net zero is this concept of society that says that they want a balance between the production and the removal of greenhouse gases. It means that if we are burning fossil fuels because of power generation, then we need to be removing carbon from the atmosphere. And this balance calls for electrification, which China is doing really well, by the way. Electrification, because if we consume power from the electricity, we know how much is coming from fossil fuels and how much is not coming from fossil fuels, and we can help in this balance of net zero. And batteries, as a way of storing energy, is a key player to help us in net zero, in the balance between the production and the removal of carbon. These are an example of batteries. So batteries are really, really important. What are the problems? That now we know that batteries have a fire problem. And let's dwell, although there are experts like Professor Wan here on battery fires. So I want to show you just one example and an overview. Battery fires happens with any type of battery, with any size of battery, and unfortunately with any type of battery technology that we had. These are sectors that had big fire problems at different years, right? For example, this was in 2003, this was in 2011, this is more recent in 2019. And these are the companies that almost go bankrupt. They almost go bankrupt because they could not handle this fire problem. These are really big fire problems. These are not small ones. These were discussed at the level of boardrooms of the corporation of what do we do with this. This is the tip of the iceberg. The problem that is happening with fires is much bigger, and it doesn't fit into the slide. But I want to show you the problem that we have. This is a beautiful electric vehicle car park. Actually, here you can see from the plate, I think it's in China. And this is the CCTV. It's not an experiment. These are actually a real event, right? So some of you might have noticed something was happening here already. So this fire, this car, this electric vehicle, you don't know it, but it's already burning. It has already ignited. It has already ignited because maybe there was an abuse condition, maybe there was a defect, maybe there was self-heating. We don't even know because it's a real event. But this battery, as you see, oh, you don't see it? Well, it is burning. What is going to happen is that by the time from the outside we know that it's burning, it's too late. No, if the video goes very slowly at the beginning, you will see how fast it goes. Imagine that we have a smoke detector up here. Now, too late. Too late. So these fires were actually happening very slowly, but they have an exponential growth. By the time we can see them, by the time our smoke detectors can detect them, that's smoke detector, they can detect that. It's too late. It's too late. Not only is fast initiation, that will be, it's not just that they initiate very fast and they challenge our smoke detectors. Our smoke detectors, the height, the sensitivity, the location, they are designed to stop fires from polymers and wood, which they initiate very slowly. They give us plenty of time to be detected. We are not fast enough when we are talking about batteries. The toxicity of the smoke, not all smoke known to humanity is toxic. Polymers worse than wood. Batteries is the next level of toxicity. It is so toxic that we just know that it's very toxic. We can not quantify yet fully how toxic it is, because the elements that the compounds that appear in the smoke and the pyrolysis gases and the off gases is a chemistry that we're not used to look into. The fire spreads faster. It develops, batteries have the ability to develop jet fires. So they don't just take the energy that they're releasing and distribute it evenly over the surface that is burning. It actually concentrates them in little gaps, little holes, and it bends and it creates a jet fire that can be up to several times the characteristic length of the battery. So you have a battery like this that is able to have a jet that reaches here, right? All the energy goes into a very specific direction. That is a concern for the battery igniting the next element that is next to it. So it creates a hazard that we are not used to, these jet fires, right? They last for long. Maybe the peak release rate is the same as other fires that we are familiar with, but they last much longer. They can actually last hundreds of times longer than other fires. They are at lower intensity at that point. So we are not used to deal with fires that last for so long. And they are really hard to suppress. Of course, the battery is designed to avoid any external agent to come into contact with the battery, particular water. We don't want batteries to get wet. Therefore, when we try to suppress, the battery is protected by humans, by engineers, not to let the water reach the battery. So because of all these reasons, I am concerned about battery fires. And I know people agree with one or two or three, but in reality, I find it difficult that there is no full agreement into the problem that we have. So I call it the triple hazard of batteries. It's not just that batteries are flammable. It's okay. This carpet is flammable and it's very safe. This boot over here is flammable. This computer is flammable. We are used to have flammable elements around us because we rely on fire engineers. Is that also it comes with an ignition source, a source of ignition next to the flammable element. The two of them packed together very nicely, right? And that when it ignites, it is faster, higher toxicity, spread, longer, and harder. So this is what I call the triple hazard of batteries. I am concerned. I'm just very happy that batteries at this point are relatively safe. And I think there is only a fire every several thousands of batteries that are manufactured, even sometimes several millions of batteries that are released. But in this room right now, right, we all have batteries. And in this room, probably it's already about 100 batteries, right? So very concerning to have this phenomena. What is going to be the solution? Well, the solution is to do experiments, to do nice measurements. There is experiments happening here in USTC. These experiments actually, in a paper that we did together with USTC, the experiments were done in USTC. So I'm really happy about this. We develop theories and concepts, and we help engineers to provide the layers of protection. We want to avoid these fires because they are bad. If we fail prevention, we want to detect them as soon as possible. Batteries have they have smart systems embedded. Not all batteries, but many batteries have management systems inside. It means that they are able to detect the fire inside the battery. They don't need to detect it outside the battery. We already saw when we detect the fire outside the battery, it's too late. We need to detect the fire inside the battery. We need to allow people to evacuate very fast, faster than normal, because the gases are very toxic. We need to rely on compartmentation. This is one, for example, one solution that they use in the aircraft industry. They have big batteries inside the airplane, and they just make sure with a steel box that whatever happens to the battery doesn't get to the rest of the airplane. So that's a compartment type of solution. We want to suppress. We don't know yet how to suppress battery fires. We're still learning, hot topic of research. And if we fail in all of the above, we need to make sure that the system, the car park, our home with the batteries, an airplane, a ship, a spacecraft is happening. As I speak, even satellites have batteries, lithium-ion batteries. There is no people, but a satellite is a very valuable device that is sent to orbit with a lot of cost, and it might be orbiting Earth for a decade. We don't want, as engineers, to have a lithium-ion battery in space because they don't need the oxygen of the Earth. The battery has a chemistry that actually has the reactants, all of them, already inside the battery. It can actually happen in space, and it could knock the satellite off. And then actually, not only we lose the investment, we lose the technology and the tool, but we actually create debris all around the trajectory of the satellite. So these are topics that maybe we were not thinking before. Fire hazards in satellites. Well, I've worked for NASA helping fire safety of a spacecraft because there is people inside and they need to breathe oxygen. But now even we remove the oxygen, we remove the humans, and we still have now a new fire problem that happens in satellites. So with this, I'm finishing. Thank you for listening to me. I just want to tell you, know the importance of being modern in our fire science and listen to society and realize that climate change, sustainability, and net zero are here and that we need to address them through combustion science and fire research. Just 3 examples. We are very concerned about the increasing frequency of destructive bad wildfires. We are concerned about the safety of tall timber to make sure that it's sustainable. And we are concerned about the triple hazard of batteries. Just as 3 examples of the many different topics that are here. I like to talk about the things that we as engineers can do to address these hazards of any hazards through the concept of the layers and see how each of us might be contributing to the technology of each or all of the layers, and that the better we understand these hazards, the better would be our solutions, and the more we will be contributing to a sustainable and safe world. So with this, I finish. Thank you very much.
Okay. Okay. Thank you very much for a very impressive talk. And to summarize this, the major challenges for the future development of fire safety science. So we can have some questions if you have. Please have any questions?
Don't be shy.
小雨，你来一个。
Thank you, Dr. Rein, for very interesting presentation. So I have a question regarding tall timber. So in China, we usually use timber to construct some temples or some historical buildings. But
Yeah.
is there any codes to regulate the timber construction in UK or in Europe? So,
Yeah.
Yeah, because in China, tall timber is basically impossible. Yeah.
So now that's a good question. So tall timber is not impossible, but really hard all around the world because of fire. So until we solve the fire problems of timber, no one will be allowed to do tall timber. So that happens in China all around the world. We have been building, everybody in China as well, ancient buildings made of timber for a very long time. Fire is the #1 cause why we lose ancient buildings made of wood, because wood is flammable. So there are codes and there are standards to protect legacy buildings, beautiful buildings made of wood, and it all requires the layers of protection. So the standards do exist. Different countries do it different ways. China does it in a way. Japan does it in a different way. But the important thing is that all the layers have to be present, and the standards should be improved. It's not just that the standards were written 10 years ago, 20 years ago, 100 years ago, and they remain cast in stone. They need to be revised. And as we learn more from our research, we could be improving those standards. So standards need to be evolving and always getting better, so we protect heritage buildings and ancient buildings also made of wood.
Okay, thank you. So another question is, have you done some experiments or simulation regarding the timber fire in your lab?
Yeah. I mean, many people have done experiments with wood. I'll tell you the latest one is that we are studying the smoldering combustion in wood. So as anyone that has a bonfire, wood that have a fire, that we suppress the flames, but the smoldering continues consuming the structure for days and even weeks. And we could actually lose the whole building, not because of the flames, but because of the smoldering. And in our group at Imperial College, we like to study smoldering, so we are also studying smoldering in timber.
Thank you.
Okay. Any other question? Please. Yes.
Thank you for your presentation, and I have a question regarding to the car fire. Like you just said, it's really hard to find out that there's a fire break out. So I'm just curious, if you put a detection like the temperature or something else to the car, will this problem be solved? Because it's pretty hard to say if this one is just like a little bit high temperature because it's usage, or it's like the temperature rise because of the fire. So I'm just curious about that, like the detection on the first stage.
Yeah, so that's a great question. In principle, you could just measure the temperature of the battery. They actually do measure the temperature of the battery already, and it doesn't work as a detection system. And the question is why? And the answer is, by the time we know that the battery is hot, because we can sense it, it's already too late. It's already ignited. This is the concept of self-heating. Professor Semenov got the Nobel Prize in physics in 1956 because of the self-heating theory of thermal runaway. And he shows that ignition is not when it's burning at a high temperature. Ignition is an imbalance of heat transfer flows at room temperature. So what happens is, and maybe they're listening, is battery technology experts that are working on batteries need to develop sensors that are not based on high temperature, but on heat transfer. So heat transfer flows, not the high temperatures.
So is there any technology nowadays to detect them?
No, because they are not reading Semenov Nobel Prize of 1956.
I see. So that's your question.
So what I tell to industry is that they should read fire science. They need to read fire science. They don't want to, battery people don't, in principle, battery people, fire people, yes, but battery people that do only batteries, they don't like to read about fire. They think that fire is too much reading. No, they think our books are too thick. They're like, I have to read all that. So, but one day battery people will read fire science and they would be, oh wow, I could use Semenov theory for detecting fires. It's like, yeah.
Okay, thank you so much.
Another question? Just a small question that you have mentioned that the good fires. So can you have more explanation about that? Good fires?
Yeah.
What's the meaning of that?
Good wildfires.
Good wildfires. Yeah.
Are wildfires that bring equilibrium to the forest. So the forest was invented by nature. Wildfires were invented by nature. And they can reach equilibrium. And a forest that is burning at the right frequency and at the right intensity will remain being a healthy forest. Then humans arrive, climate change arrive, land change arrive, and we alter the frequency and intensity of these wildfires. Then the forest is unhealthy and it starts to burn.
I see.
If we bring back the good fires, which are low intensity and the frequency the forest needs, then the back goes back to healthy. And it is sometimes burning a little bit, but it's healthy. Supposed to the extreme of this is fire exclusion. If the fire never burns, it has not burned for 40 years, then that's very concerning, because maybe that forest needs to burn every 5 years, every 10 years. Sometimes in the Arctic, they're supposed to burn every 200 years. But if we exclude fire, then the fires become all of them bad fires.
Okay. So another question is that for the wildland urban interface fire, you know that kinds of fire is very typical in America and also in Europe and Australia. But I think you should notice that it's not very typical in Asia.
Yeah.
So what's the major reason, do you think?
You mean the wild-urban interface?
Yes.
Well, maybe some communities have been able to, the interface between where people live and where the forest is, it exists everywhere. If fires are not crossing the interface, that's good. The question is, for how long is going to be that good? Because once upon a time, wild-urban interface fires didn't exist in the United States. Maybe 200 years ago, they didn't have that problem. It was not a concept. So the Americans, the North Americans, were the first ones to create the concept when they realized fires that are hopping in the forest are crossing into people. If it's not happening in Asia, that's good news, but I will suggest that you learn all the lessons of what could go wrong so that it never happens, or that if it happens, you are prepared for it.
Okay, so how about the impact of the climate difference? For example, in China, and for the same attitudes as California, so but different climate. So do you think that's the very important reason for the difference fire frequencies of the China and the California?
Yeah. So the problem with wildfires, the causes of wildfire behavior changes is, as I tried to explain here, is very complex. This is very complex interface, and this is a simplified reasoning. In reality, there are even more reasons. So it's very complex. I think it is important to know all of the above. So China has different ecosystems, has different effects on climate, has different culture, has different locations of population. So each country will have a different wildfire problem because each of these things are affecting them in a different way. So each country has to learn the ecosystem, the weather, the culture, the population of their country. And where science solutions will be the same, the science will be the same or similar. The way we implement this in each of our countries will be different.
Okay, thank you. Another question? Okay. 问题是他谈到了这个吗？
对，他在问光会有什么方式。
这个有点太普通，他这个报告里头没提到这个，主要是提到就算。Okay. Another question, please.
Guillermo, thank you very much for your nice presentation, a lot of insights. My question is that in your title you mentioned combustion, but I find for example Biography, the combustion very important.
Yeah.
You are say the crossroads for combustion in viruses. And you also mentioned that the building damage resistance is also about structural part. So can you explain more about combustion role in this crossroads?
Yeah, so all the problems that I've mentioned are combustion problems. Because we want to avoid them, that becomes fire science. So the combustion that we want, the wanted combustion, so to speak, because we want higher efficiency or we burn faster engines, that's a branch of combustion that doesn't deal with fire. But when we want to stop combustion from happening because it's hurting us, our properties, homes, or the environment, that has become the realm of fire science. So all these topics are related to combustion with a specific view of fire science. And batteries, I cannot stop the video now. Let me see if I can stop it, because I want to make the point. No, it's okay, I can't. But anyway, so in this particular moment, for example, you don't see a flame. And some people say there is no fire because there is no flame. Yeah, no, I'm an expert in smoldering combustion. Smoldering doesn't have a flame. Yeah. Smoldering is a fire. It just doesn't have a flame, but it's an undesired, fast release chemical reaction, exothermic. That is a fire. Battery, it doesn't have, it's not consuming, it doesn't have entrainment, it doesn't have a flame. It is a fire. It's 100% a fire. Is a new type of fire that humans have created? Yes, for sure. Is it unwanted? It is exothermic. It is fast. For me, a lithium-ion battery igniting, it's a fire. Even if it doesn't have a flame yet. It will have a flame later on. But even when it doesn't have a flame, it's a fire. So many people say that battery has not ignited yet. It's just thermal runaway. But because I've read 1956 Nobel Prize of Professor Semenov, I know that thermal runaway is the same as ignition, and it doesn't have to have a flame to be a combustion topic. So all these are combustion topics.
Even before the flame ejected,
for me, yes. Fire, like for me, for Semenov, Professor Semenov, and Professor Frank Kamenetsky, for Professor Juan, for us, it's a fire. It doesn't have a flame yet, but it's a fire.
Yeah, just want to convince ourselves.
Yeah, and it's combustion of a different type of chemistry. It's not hydrocarbon combustion. It's not oxygen-based combustion, but it's combustion.
Okay. Any other question? Yes.
Thank you, Professor, for a wonderful presentation. So you talked about different layers of fire protections, and you also talked about sustainability, which involves economics. So can you further comment on that these different 6 layers, how much economics they are involved to achieve the sustainability? Thank you.
Well, that's a good point, actually. So let's go to the sustainability one. Sustainability, because you asked specifically about, so in sustainability, I use the example of timber. So all these layers, the more layers we have, and the better each of the layers is, we are delivering protection. So protection is, this is the hazard, this is us, and the more things we put in the middle, the better, right? So if one of these layers fails, it's okay, because the other layers will help. If all the layers fail, we have the fire already damaging life, affecting life, property, and the environment. So, and the question is, if we have all these layers, it becomes very expensive. So it's not sustainable because it's not balanced with the economy. But this is what engineers have been doing for a very long time, is that if you cannot afford these layers because they're too expensive, it means that they are not efficient. So we need to do more research to make these layers not expensive, but affordable. So part of sustainability is making sure that these layers are good and inexpensive. If one of these layers, for example, not in timber, imagine that someone comes out with an amazing coating that you put on timber and it makes timber zero flammable. It will be amazing, but it costs more than the timber itself. It will not be sustainable. We have a technology, but it will not be sustainable because the building will be so expensive, it's not balanced. It has to be an amazing coating that we put on the wood and it's not as expensive as the wood itself. And that would be what you are referring to, is a true balance between the safety, the economy, and the quality of the building. So cost, affordability is part of sustainability.
Thank you, Professor. I have a question about the welfare. In the layers of welfare protection, you have mentioned that we need some boosters. We need some boosters, and we should avoid the bad welfare. So I wonder, how can we distinguish welfare, whether it's booster or bad?
Yeah.
When it's ignited.
That's a really good question. Professor Liu already asked this question. I asked that question to myself as well. So imagine that it's a fire and we detect it. Is it a good fire or a bad fire is what you're asking. And that requires not just engineers. It requires knowledge of the forest. It requires knowledge of what's burning, because we need ecologists to tell us that type of ecosystem, that type of beautiful forest in the mountain is not meant to burn more than once every 10 years. And it has to be fires that happen in the spring, because they are light intensity fires. This fire happening in the summer, suppressed, is a bad fire. This fire is happening in the spring. And when was the last time this forest burned? Oh, it just burned 20 years ago. Okay, then maybe we might be a good fire. And it's the springtime. It's a small fire. It's propagating slowly. So keep monitoring the fire, but let it burn. Don't suppress just yet. Right? That's this is what they do in the United States. In the United States of America now, they don't suppress all fires. They suppress all the fires in the summer, but some of the fires that happen in the spring and in the fall, if they're away from people, they let them burn for a little bit at least. And obviously they keep an eye on it. They monitor the movement of the fire. Because it could be that it's a good fire that is removing the fuel and is regenerating the forest and is allowing the new species to come back, and it might be actually destroying the species that are invasive and they're not part of that forest. So that's a very good question. It requires the collaboration of engineers and ecologists together, talking to each other.
So we can also use some methods such as prescribed.
Yeah. So thank you. Good question. So it's not that avoiding ignition or not, is promoting good fire. So if we know that an ecosystem has not had a good fire for a very long time, what we do is we bring the fire ourselves. So we prescribe a burn. We actually burn the forest on purpose, but we do it on our own terms. We do it when it's safe, when there is no wind, when the forest fuel is not too dry or not too wet. We do it in a way that we can detect the fire going across. We do it when the smoke is not going to bother people, and we do it when it's safe. And when all these conditions are met, we can bring the good fires back to our forest. It's the concept of prescribed burning. The Americans, in America, which we humans have been doing prescribed burning for thousands of years, millennium, probably, millions of years. But now it's a scientific topic. Prescribed burning as a scientific topic is a topic that we study often in many different countries, and I'm sure that China should be looking into this at some point, because it's controversial. If we leave this building and we tell people in the street that sometimes we ourselves have to burn the forest when it's safe and right to do so, people will be in disbelief. at least in my home country in Spain, people will say, no, burning the forest is bad. And the answer is, will scientists have learned that not always is bad to burn the forest. Sometimes it's bad not to burn the forest, right? The concept of fire exclusion. And knowing the difference requires understanding, requires science, requires communications, integration, and exchange.
But often we cannot control the fires completely.
So a prescribed fire,
prescribed fire,
ideal prescribed fire is only light when we know we can control it. If we don't know if we can control it, in principle, we should not be starting the prescribed burning.
Yeah, you know that almost 10 years ago, the Chinese, some forestry management departments, they used the prescribed fires, but nowadays they don't dare to do that.
Yeah.
It's very dangerous.
Well, we know from Europe and from the United States that the idea of prescribed burning gets scientists very happy about it, right? So sometimes we've convinced, not me myself, but other scientists have convinced managers and they have done it. And when it goes well, it's great. When a prescribed fire runs away and it becomes a wildfire and burns a community, then no more prescribed burning for 10 years. Because everybody now is very concerned about that one time that it went wrong.
Yeah.
So, but we are engineers are familiar with having a system that is safe. So prescribed burning is difficult, it's very important, it requires understanding, and it should only be done when we know that it's not going to fail.
Okay, thank you.
When you say that it's a good fire, but still it will cause harm to the environment, to the climate. So
but
then how we will achieve net zero from a good fire?
No, actually, this is fascinating. Remember, fires were happening even before we became a species, and the planet was not was going global. It didn't have an excess of carbon fossil fuel in the atmosphere. So if you burn a forest and you let it grow back within 7 years, the wildfire has become a carbon neutral process because the carbon that it released in the fire has been captured by natural means back into the biomass that grows again. If there is a wildfire and we don't let it grow back again, then the wildfire has become a net contributor to carbon emissions. So what is important is that a wildfire doesn't mean all the carbon is already in the atmosphere. It means we need to make sure that the forest grows back again, maybe even healthier than before, so it captures back the carbon that it released. And we have 7 years to do this. After 7 years, the climate has already felt the emissions, and it starts to become not a neutral process. And in this context, for example, burning an ancient forest. In China, you have ancient forests. Forests that are really, really old, right? Some of those trees have hundreds of years. If it burns, and it took 100 years to grow, it is a carbon emitting process because you cannot grow back an ancient forest in 7 years. So ancient forests have to be, or ancient trees in a forest have to be protected. They should not be allowed to burn because we cannot grow them back in 7 years. Grasslands, bushfires, heather, the type of vegetation that can grow very quickly, small trees that can grow back in 7 years, those we can lose because we grow them back again and it becomes carbon neutral.
Okay, so if we have no more questions, so let's thanks again for the very great talk of Professor Guillermo Rein.
Thank you.
那行，今天的报告会就到此结束，好，谢谢。这个好像。